Welcome back to the Victory Education Lounge, everyone. I'm your host, Maurice, and today we're diving into part 9 of our series on insulin resistance. Before we begin, please take a moment to like this video, subscribe to our channel, and leave a comment sharing your thoughts or experiences below. Your engagement helps us reach more people with this vital information. Today we're exploring the hormonal havoc, how insulin resistance disrupts balance. We'll delve into the intricate web of hormonal interactions in our bodies and how insulin resistance can throw this delicate balance off kilter. We'll also discuss solutions, management techniques, and prevention strategies, along with their pros and cons, and provide real-life examples to illustrate these points. Ever pondered over what happens inside your body when insulin resistance develops? Well, you're about to find out. Insulin resistance, a significant health concern worldwide, is a condition where the body's cells become less responsive to the hormone insulin. But what is insulin, you may ask? Simply put, insulin is like a key that unlocks the doors of our cells, allowing glucose from our bloodstream to enter and provide energy. However, in insulin resistance, these cellular doors become less receptive, making it more challenging for the key to perform its job. As a result, glucose builds up in our bloodstream, leading to high blood sugar levels. This process can eventually lead to type 2 diabetes and other health complications if left unchecked. Now that we've established a basic understanding of insulin and insulin resistance, let's delve deeper into the biochemistry of insulin resistance. When insulin resistance occurs, the insulin signaling pathway is disrupted. This disruption is not as simple as a traffic jam or a blocked pipe. It's a complex sequence of events that can have far-reaching effects on the body's ability to process glucose. Let's break it down. Normally, when insulin arrives at a cell, it attaches to a receptor, like a key fitting into a lock. This triggers a series of protein interactions that form what we call the insulin signaling pathway. This pathway, in essence, gives the green light for glucose to enter the cell, providing it with the energy it needs to function. However, in the case of insulin resistance, this pathway doesn't work as it should. The key, or insulin, doesn't fit the lock, the insulin receptor, as comfortably as it should. The result? The green light flickers, the pathway is disrupted, and glucose struggles to enter the cell. Imagine Sarah, a 45-year-old office worker. Her cells are like locked doors, and insulin is the key. But with insulin resistance, Sarah's locks become less responsive to the key, making it harder for glucose to enter her cells. It's as if Sarah is trying to unlock a door with a key that no longer fits perfectly. This is just one part of the complex puzzle of insulin resistance. Understanding this process is crucial in managing and potentially reversing the condition. Now let's move on to the role of GLUT4 in insulin resistance. The GLUT4, a protein that helps transport glucose into cells, doesn't function effectively in insulin resistance. Now imagine GLUT4 as a fleet of delivery trucks. Their job is to carry glucose, our body's primary source of energy, into cells where it's needed. In a healthy body, these trucks move efficiently, delivering glucose promptly from the bloodstream to the cell. However, in insulin resistance, it's as if these trucks have faulty GPS. They can't find the cell surface or loading dock as effectively, meaning less glucose is transported into the cells. Let's take John, a 50-year-old teacher, as an example. In John's case, his GLUT4 trucks aren't reaching the loading docks as efficiently. This reduces the amount of glucose his cells can take in, leaving more glucose circulating in his bloodstream. Next, we'll explore how inflammation contributes to insulin resistance. Chronic low-grade inflammation can contribute to insulin resistance by interfering with insulin signaling. Inflammation, as we know, is the body's natural response to injury or infection. But when it persists over time, it can create a state of chronic, low-grade inflammation. Now imagine Maria, a 38-year-old chef with a high-stress lifestyle. The stress in her life triggers an inflammatory response in her body. This inflammation can disrupt the normal functioning of insulin signaling. It's like adding roadblocks on a highway. The insulin, or key, still exists, but its pathway to the cells, or doors, is obstructed. This disruption can lead to insulin resistance, where Maria's cells don't respond properly to insulin. As a result, glucose can't enter her cells as efficiently as it should, leading to higher blood glucose levels. Understanding this connection between inflammation and insulin resistance can help in developing strategies to manage and potentially reverse insulin resistance. Now, let's take a look at the role of free fatty acids in insulin resistance. Elevated levels of free fatty acids in the bloodstream can interfere with insulin signaling and glucose uptake. These fatty acids, often the result of a diet high in fats, can disrupt the normal functioning of insulin in the body. Imagine our friend Tom, a 55-year-old businessman who enjoys a diet rich in fatty foods. When Tom consumes these foods, his body breaks down the fats into free fatty acids. These acids circulate in his bloodstream and can interfere with insulin's ability to do its job properly. How does this happen? Well, when there are too many free fatty acids in the bloodstream, they can accumulate in other tissues, such as the muscle and liver. This accumulation can cause these tissues to become resistant to insulin, meaning they don't respond to insulin signals as well as they should. Next, we'll explore how mitochondrial dysfunction contributes to insulin resistance. Impaired function of mitochondria, the cell's energy powerhouses, can contribute to insulin resistance. Now, you might be thinking, wait a minute, aren't mitochondria those bean-shaped things from biology class? Exactly. They are the structures within our cells responsible for generating most of the cell's supply of adenosine triphosphate, ATP, which is used as a source of chemical energy. So how does this tie into insulin resistance? Well, in a healthy state, mitochondria in our muscle cells are busy converting glucose and fatty acids into ATP. But when insulin resistance sets in, this process can get disrupted. Instead of producing ATP, the mitochondria might start producing reactive oxygen species, or ROS, which can lead to oxidative stress and further exacerbate insulin resistance. Let's take Lisa, a 40-year-old nurse with a sedentary lifestyle, as an example. Lisa's mitochondria aren't as efficient as they could be due to her lack of physical activity. This inefficiency can lead to a buildup of glucose and fatty acids within her cells. And as we just learned, this can lead to an overproduction of ROS and further insulin resistance. So, what can Lisa do? Well, regular exercise is a great way to boost mitochondrial function. By getting up and moving, Lisa can help her mitochondria more effectively convert glucose and fatty acids into ATP, potentially reducing her insulin resistance. Now let's delve into the role of endoplasmic reticulum stress in insulin resistance. ER stress can trigger cellular responses that interfere with insulin signaling. Now, let's delve into the role of endoplasmic reticulum, or ER, stress in insulin resistance. The endoplasmic reticulum is a network within our cells, acting as a production line for proteins and lipids. When this system is overwhelmed, it triggers ER stress, which can disrupt insulin signaling. Think about David, our 60-year-old retiree with poor sleep habits. Sleep deprivation can cause an increase in ER stress. In David's case, his cells' production lines are running overtime, leading to a backlog. This backlog, or ER stress, can cause a cellular response that interferes with insulin signaling, making his cells less responsive to insulin. This is like a factory that's overwhelmed with orders and can't keep up, leading to delays and mistakes. So it's important to manage ER stress to maintain proper insulin function. Next, we'll explore how oxidative stress contributes to insulin resistance. Excess free radicals can damage cells and contribute to insulin resistance. This is the process of oxidative stress, a vital player in the biochemistry of insulin resistance. Free radicals, or rather reactive oxygen species, are naturally produced in our bodies. However, when their numbers surge beyond what our bodies can handle, they start causing damage, effectively rusting our cells from the inside. Think of Emma, a 35-year-old smoker. Her lifestyle exposes her to an excess of free radicals, which can cause havoc on her cellular machinery. The oxidative stress inflicted by these radicals can disrupt insulin signaling and glucose uptake, contributing to insulin resistance. Remember, oxidative stress isn't just about smoking or exposure to pollutants. It can also stem from poor diet, lack of exercise, and chronic stress. In the grand scheme of insulin resistance, every piece of the puzzle matters. Oxidative stress is one such piece, and addressing it can be a significant step in managing insulin resistance. Last but not least, let's discuss adiponectin and its role in insulin sensitivity. Adiponectin, a hormone produced by fat cells, improves insulin sensitivity. However, in insulin resistance, adiponectin levels often decrease. Picture adiponectin as a mediator, bridging the gap between insulin and the cells it needs to reach. In a well-functioning system, adiponectin ensures that insulin can do its job effectively, helping glucose move into the cells smoothly. But what happens when insulin resistance kicks in? Well, adiponectin levels tend to drop. It's like losing a crucial team player in a relay race. The baton, or in this case glucose, doesn't get passed along as efficiently. This drop in adiponectin can further exacerbate insulin resistance, creating a vicious cycle. Consider Jane, a 30-year-old athlete with a balanced diet and regular exercise routine. Jane's adiponectin levels are likely healthy, aiding in her body's insulin sensitivity. However, a sedentary lifestyle or poor dietary habits could risk lowering these adiponectin levels, making Jane's cells less responsive to insulin. This concludes our exploration of the biochemistry of insulin resistance. Stay tuned for our next video, where we will discuss solutions, management techniques, and prevention strategies for insulin resistance. Thank you for joining us for this exploration of the hormonal havoc caused by insulin resistance. I hope this information helps you better understand the complex interplay of hormones in your body and empowers you to take control of your health. Remember to like this video, subscribe to our channel, and share your thoughts or experiences in the comments below. Stay tuned for our next video, where we'll explore the link between insulin resistance and various health conditions. The information provided in this video is for educational and entertainment purposes only. It is not intended as medical advice or to replace consultation with a qualified healthcare professional. Always consult your doctor before making any changes to your diet, exercise routine, or starting any new health regimen.